Came from a meeting at Pitt and ran a good part of the way. I want to just first retouch something we discussed last time, which is conjugate priors. So the general definition of conjugate priors is a family of priors, say family F, this would be a different, this would be, Yun, what symbol do we usually use? Oh, what do you usually use for hyperparameters? Alpha? All right, maybe a family F alpha of priors. So it's a set of priors parameterized by some one or more parameters alpha, is conjugate to a family this is F, I don't know, call it G, I don't know, G of likelihood functions. So maybe make the notation a little more elaborate. This would be F of theta sub alpha. And this will be G of the data condition on alpha and theta. I guess you can put the conditioning thing here, you can put it here, and you'll see people doing it both ways. Let's first see what it means. This is the usual, maybe I'll call it L, just to confuse you, to remind you that it's likelihood.
Alpha does not appear in the expression of L.
Yeah, it doesn't. That's why I'm, yeah. All right. Let me try to make it uniform thing. Okay. So the picture is there is some prior distribution, pi, that gives us theta. So you sample from this distribution and you get a set of thetas. And once you got a particular, you get a single data point consists of multiple thetas. You get one point in high dimensional space, which is theta. And then once you got that point, it defines for you a distribution, a likelihood distribution of the data given the theta. And now you generate data from it. Okay? This is the classic two-step Bayesian view of the world. Now I could write it like this. Theta is drawn from a distribution over theta that is parameterized by some parameters alpha. So I mean the same thing here as I mean here. So it is drawn from this distribution. This is a distribution over possible thetas characterized by some parameters. And it gives us this particular theta. And then the data is drawn from this distribution parameterized by theta. So there is alpha leads to theta leads to data. You can imagine this can become very rich if the story you tell is that you first drew one set of alphas, call it alpha 1 or alpha A, and generate a lot of data from it, and then you drew another set of another theta, which is theta B, because it was a different independent draw from the prior, and then you collected a lot of data here, and then you drew another one and you collected a lot of data here. Or you could even say that you first drew n of those, and then you chose Each data item could come from any one of them. You can create a lot of structures from that. But in the simplest case is just you draw ones from the prior, you get the thetas, and then all of your data comes from that theta. What else do I want to say about that? Let's give an example. So, flipping of a coin. Example, probability of head in a coin. So the probability of head itself is theta. The theta bar, the array, is just a single parameter, theta or theta head. The prior over all possible values of theta head is anything we want it to be. We said that if the coin came from a normal factory that makes regular coins, it's probably going to be very close to 0.5, right? But maybe not exactly 0.5, so it would look like something like this. So the family is the family of all distributions over all densities in the range 0 to 1, of which there are infinitely many. I can choose a particular family of densities, let's say Gaussians. So I could say that F would be the normal distribution parameterized by alpha 1 for the mean and alpha 2 for the standard deviation. So the mean and the standard deviation could be anything. But once I fix them, they could represent this particular Gaussian. Say this alpha 1 is 0.5. And alpha 2 might be 0.1. This might be 0.1 here. So for a particular choice of the alpha parameters, now I get a prior, a particular member of the prior family. I get a particular prior from which I draw the probability of head for every coin that comes out. So now a coin comes out, it could have been anywhere here, but it's most likely to be around here. And I can flip it many, many times and get data that depends on its true theta. Another coin comes out, it might have a different theta. Here, this whole picture is called the Bayesian hierarchical model. Bayesian. And hopefully you can see if you had enough coins generated from the factory and each coin was flipped enough times, you could estimate not only the true theta for each coin, the true probability of head or how biased it is for each coin, but you can also start thinking about estimating the underlying distribution of the priors, namely estimating the alpha 1 and alpha 2. More than that, suppose you had many, many coins, but each one was flipped only a small number of times, 5 times. If you estimated the theta for each coin just from the 5 flips of that coin itself, your result would be not very good. It would be high variance in your result because there were very few. But the fact that you know that all the coins come from the same source should help you. So this is related to Stein's paradox. You can shrink your estimate for a particular coin with the flipping of the other coins. You can think of the result of flipping the other coins as an estimator for the coin you're interested in. It's an estimate that has some bias, but it has reduced variance. So by shrinking it together, you could potentially get a better answer. And you could do it using the frequentist way of just linearly combining, or you can do a complete Bayesian analysis and come up with a joint maximum likelihood estimate of the entire system. So we're not doing any of that. I just want to impress upon you that this view is very powerful. This Bayesian hierarchical view is a very powerful view for combining evidence data from many different sources, and how flipping this coin can actually gives you some information about the true theta of this coin. Actually, more accurately, not flipping one coin, but flipping many, many coins that came from the same distribution will tell you something about this coin. Okay, so now I can go back to the notion of conjugate. So we have a family of priors. For example, this one, parameterized by some parameters alpha. And when they are used with a family of likelihoods that are parameterized by the theta, so here is the particular prior that comes from that family. And it goes into the Bayes engine. And do you remember what else comes into the Bayes engine? First you have data coming in, and then there's a particular likelihood function. And the likelihood function you can think of, it's not one particular function because it depends on the theta, it's a family of functions. The binomial distribution is a family because it depends on the probability of head. The Gaussian is a family because it depends on mean and standard deviation. Out comes a posterior. This is a prior. Out comes a posterior, which is P of theta giving the data and giving this assumption of the likelihood. And now we're ready to define what a conjugate prior is. A family of priors is conjugate to a family of likelihoods if, whenever your prior is a member of that family, and your likelihood function is from this family, then the posterior is automatically guaranteed to be another member of the original family F. This also belongs to F. So if the prior is a member of the family, then the posterior is a member of the family with different alphas. With, in general, different alphas. Might be the same, but. So remember that a prior and a posterior are almost the same creature. They're both ways of summarizing everything you know and believe about the world. Summarizing your belief about how likely different latent scenarios are. The difference between them is one is before you saw the current data, and the other one is after you took into account the current data. But after you took into account the current data, if you're about to take into account tomorrow's data, then what today was your posterior, tomorrow will be your prior, right? So it's really the same kind of thing, it's just updated. So this is your beliefs updated up to this point, and this is your beliefs updated up to this point. So this is why having a conjugate prior is such a powerful tool, because it says that if you start from an assumption that assumption about the world that is captured by one member of this conjugate family, then it will computationally be very easy for you to update it. Because you know that whatever data you see, it doesn't matter what data you see, you will end up with an updated, with a posterior, that is another member of the same family. And often we can derive exactly the relationship and tell you, given your initial alphas and given your data, what your final alphas should be. And that's exactly the situation with multinomial. Yes?
Is it possible to have a non-conjugate likelihood function you could use instead, so this property wouldn't hold, so your prior would not be from the same family as your posterior?
It's certainly possible. You may run into a computational problem that you don't know, or a mathematical problem that you don't know how to solve the integral that's involved. Remember, there's an integral involved here, right? So it's possible that you could solve the integral. It's possible that you'll solve it numerically, then you don't care. But the nice thing about it is that it's computationally very easy. You don't need to actually solve the integral. You know the solution. It's analytical, and you know where it will end.
Okay.
Yes.
So the prior and the posterior are in the same family. Are we saying the priors are conjugate to the posterior, or
No.
to the likelihood?
To the likelihood. So given the likelihood function, this family of distributions over theta, a family of priors, you can call it, is conjugate to it if whenever you start with a member from that family, you'll end up with a member from that family. I should say it explicitly. F is conjugate to L if and only if for every I can call it pi in F, pi in F, the probability of theta conditioned on the data and the prior being pi is also a member of F. Question?
So you see often in language technologies models using Dirichlet or priors because they're convenient and they have they're conjugate to a certain class of functions.
They're conjugate to multinomials.
Yes. How do you justify this in terms of the properties of language? And
Right. So it's a very good question. All I argued here is that this prior is very convenient. I didn't argue that it's good or appropriate or the right prior, if there is such a thing, or that it makes sense for language. And the answer there is that the Dirichlet family is quite a wide family, quite a rich family. So you can choose many different initial alphas, and you can express many different beliefs that you have a priori about language and about the domain you're in. It's not everything. Of course it isn't. If it was everything, it wouldn't teach us anything. I mean, priors have to be somewhat informative. But it's very rich. There's some things it cannot capture. But there are many things it can capture. And the examples I gave you last time of those little mounts we saw in the 3D display tries to capture that you can bias it towards one word being more, if you remember the x1, x2, x3, and you can say x1 is likely to be high, x2 is likely to be low, and you can have different standard deviation. I can tell you the standard deviations are all tied together in a way that's hard to decompose. It's also hard to express things like Zipf's law, namely that there's going to be a few words that are very common and the rest are very uncommon. It's hard to express that without choosing which ones are common, which ones are not common, right? I mean, you can say x1, x2, and x3 are going to be high values and the rest are going to be low values. That you can easily express with the Dirichlet because you put the peak of that right near them. But it's hard to express. It could be near any combination of three. So there are always going to be things that are easy to express and things that are hard to express. Yeah, and sometimes other priors would be more appropriate. Yes?
Just as like a thought on the trying to estimate like Zipf's law on a corpus of words, or like a vocabulary. What if you had like a different learning step where you would try and learn the like ranking of words to pick, and you like your Zipf's law curve would be fixed, and you'd be trying to like fit like a list of words, but trying to figure out the order of words that would fit that.
Right. So that would correspond to something like a rank prior, like a prior over the ranking, right? I don't know much about it, but it seems like a reasonable way to think about it. Okay, so let's take an example. We said that the Dirichlet theta can come from a Dirichlet distribution with alpha 1 through alpha n. And remember what this Dirichlet, what the alphas mean in a Dirichlet. First of all, the larger the alphas, the broader the prior distribution over the space of all multinomials is. The standard deviation is much larger. As alphas go to infinity, this distribution tends towards a I guess, a uniform distribution over the entire simplex. Is that right? No, it's the opposite. It's exactly the opposite. What am I saying? As alpha goes to infinity, it lends towards a very peaked distribution. Where is the mean of the distribution? So the mean for each theta I, we said is alpha I over the sum of the alphas. And the mode of theta I is alpha I minus 1 over the sum of the alpha minus 1s. I always confuse the two, so Yun Haiju, you're here to correct me. Did I get that right?
I think so.
Okay. So in the simplest case of if the alphas, alpha 1, alpha 2, alpha 3 are 1, 2, 1, that means that they sum to 4, so it's a quarter, a half, and a quarter. So it's as if you had a vocabulary of 3 words, and the mean of the prior over all possible distributions of all these 3 words was assigning a quarter to the first word, a half to the second word, and a quarter to the third word. That doesn't mean that every time you draw from that prior you will get this. But it means this is sort of the average numbers you will get. So if you look at it as a little pile, like a Gaussian, nice Gaussian sitting on them, that Gaussian center would be, the center of gravity would be at this point. Whereas the maximum would actually be at 0. This is 0, 1, 0. So it's 0, 1, 0. So it'll be a skewed kind of distribution. And I'm not sure what happens when these numbers are less than 1. I get a negative for the mode. Does that make sense?
You don't get negative for the mode because you have to normalize them.
Oh, the thing will be, well, you still get negative for some of them. For example, if,
Yeah, there can be a problem.
if this is half. All right, I don't know what it'll do. When these numbers are less than 1, generally you get this concave behavior. You get the behavior where you have higher values near the edges. Rather than a mountain, you have a valley.
In that case, there may not be a mode because you have higher values at the corners but low values in the center. So
Right, but that's why it's called a mode, not necessarily a max. It would still give you, yeah, so the formula might be a little different when they're,
yeah. So
And there.
this formula for the mode may have a range on alphas.
okay, that might be it. Anyway, so you have this kind of, you have a probability simplex which I'm drawing here in 3D because I can't draw it any higher. And to remind you, the probability simplex is such that every point corresponds to a particular multinomial. So this is a space of all multinomials, and then the Dirichlet is a PDF sitting on top of it. So in this case, it would be the mean of that distribution would be a quarter distance from here, and a half from here, and a quarter from there, whatever it is. Would be like here. But the mode would be sitting right on the edge here. It would be a tilted thing. Okay, now this is a prior that exists regardless of the multinomial. It's just a prior on the thetas. Now when you combine it with the likelihood function, which is the multinomial function, multinomial of the data given theta is defined as product of the likelihood of each individual item, and each individual item, xi, is defined as theta I to the delta function of xi and what do I call the category? Word I. So this is basically 1 if xi is word I and 0 otherwise. I just invented this notation quickly to say that it's defined as the product of the appropriate thetas along the way. In the binary case, this degenerates into theta head to the power of count of heads times theta tail to the power of count of tails. And then theta tail is 1 minus theta head, and you get the familiar expression for binomial. So now, since I know that Dirichlet is the conjugate of the multinomial, I know that the posterior given some data conditioned on theta being theta coming from the Dirichlet with alpha 1 through alpha n, I know that the posterior of this would be also a Dirichlet, and I know in advance what the parameters of this Dirichlet are. If the data has values C1 through Cn, these are the counts, then the resulting Dirichlet has parameters alpha 1 plus C1 all the way through alpha n plus Cn. So it's a beautifully simple recipe for updating the prior into a posterior. Basically take the counts of your data and add them into the alphas. So now I can go back to my pseudo-count method and reinterpret it in Bayesian terms. To remind you, the pseudo-count method was the method of smoothing a multinomial by putting some initial pseudo-counts, fake counts, into the buckets, as if they were there. We said the simplest method was to add 1 to each category, right? Every word that in fact, every word, whether you saw it or not, you start its bucket as if you saw it once, right? And then we said you could add half, you could add any number you want. Now we can interpret it through a Bayesian way of thinking. The pseudo-count method smoothing method is equivalent to assuming a Dirichlet prior. So the pseudo-count smoothing method with pseudo-counts alpha 1 through alpha n. So remember in the original smoothing we just said add 1 to everything. Just put 1 everywhere. This is effectively as if you are assuming a prior, which is a Dirichlet with 1, 1, 1, 1, 1. And then you take your counts, you throw them into the same buckets. And then the Bayesian will take the result, which would be a Dirichlet with C1 plus 1, C2 plus 1, Cn plus 1, these ones. A Bayesian would be happy here and would say, this is my posterior, that's what I keep. Because Bayesians only deal in posteriors. They don't deal in point estimates, right? But a point estimator will take this and now take the maximum likelihood. Well, if this is the mean, I guess it takes the mean of the posterior. So it's, and take the mean posterior. Remember that a non-Bayesian who is willing to provide a point estimate has multiple choices when they are given a posterior. They can provide the maximum of that posterior. They can provide the mean of that posterior. They can provide the mode of that posterior. They can provide all sorts of things, right? I mean, the mean, mode, what do we say, the median. So if you chose to start with a Dirichlet and you then provided the mean of the posterior, that mean would be Ci plus 1 over n plus v, right? Be this normalized. And that's what the pseudocount method does. So the pseudocount method, which everybody uses sort of naturally, can be interpreted as assuming a particular prior. If you use it with pseudocounts of 1, the prior you're assuming is this prior. And what is this prior? Where is the mean of this prior? Uniform. So you are choosing a prior whose mean is uniform and whose standard deviation is pretty large because these numbers are small. Because these numbers are small. Now suppose you believe that the language you're about to observe is really uniform. It's very close to uniform. You would want to tighten your prior to reflect that. So you want the prior to be more concentrated around the uniform point. You would do that by increasing the alphas. Right? You could increase it to an alpha of 50, 50, 50. At every point you give a pseudocount of 50. That corresponds to assuming a prior that is more centered around the uniform point. The uniform distribution is a point in that space, right? So centered around that point. And it's also consistent with your intuition that if you start with pseudocounts, large pseudocounts for everybody, then for the same amount of data, you would make less of a difference. Right? So this estimate would be closer to uniform if this is not 1, if this is k, v times k. The larger the k is, the closer it is to uniform. In the limit, when k is infinity, it doesn't matter how much data you add, how much finite amount of data you add, this will remain uniform. This corresponds to a prior that is so peaked around the uniform distribution that it doesn't matter how much data you put in, the posterior will remain there too. Of course, usually we do it the other way around. The prior is fixed and then we let the data grow to infinity. But here we're contemplating a series of priors that get more and more peaked around, for a fixed data set, a series of priors that get more and more peaked around the uniform. Questions? Okay, so yes, please.
One more conceptual sort of thing. Does that mean that the exact center point in our simplex would be the uniform distribution if all the alphas are equal? So I'm trying to imagine, like, when we were talking about 1, 1, 1, is it still a little bit of a bump in the middle, and then like the uniform distribution would be the exact center, and like the 50, 50, 50 would be just a very deep simplex, or?
So here's the simplex,
Yeah.
and this point is the uniform distribution.
Okay. If all the alphas are equal, right?
And when all the alphas are equal, and I'm sorry, when all the thetas are equal.
Or, okay, all of it is equal.
Now, as you move in this probability simplex, the thetas change, right? They always sum to 1. In the center, they're all equal. They're a third, a third, a third.
Okay.
Now, the alphas correspond to the mountain that forms about it. If all the alphas are equal, you have a symmetric mountain whose center of mass is right on this point, but it's distributed around it.
Okay.
And if it's 1, 1, 1, it's a very mellow mound. If it's 100, 100, 100, it's a very steep mound that most of the mass is concentrated right around here. And there's very, very little mass here. Yes.
In your example, what happens to the mode when you choose a prior with alpha 1, alpha n all being 1? The mode is undefined, right?
Yeah, that's why I don't trust that function for the mode.
Okay.
Is it because it's uniform?
Yes, if the alphas are all 1, then it's just a uniform prior.
Okay, so that's correct what I just said earlier. If it's 1, 1, 1, the mound is
There's no mount.
0. There's no mound.
Okay.
So it's completely uniform, and therefore there is no mode. If alphas are less than 1, there's actually a negative mound. It's biased away from being uniform, towards being non-uniform, towards the edges.
Yeah.
And the closer alpha is to 0, the stronger that bias. So if alpha is like 0.000001 for all the alphas, then all the mass is concentrated. I don't know if it's concentrated in the corners or here. I'm guessing it's concentrated in the corners, but I'm just guessing. Yes?
So the corners cannot be actually reached because there will be zeros, and so what's the number of 0 to the power of 1 or 0 to the power of 3, or is it something defined by the limit?
Zero to the positive power is 0.
Right.
Zero.
Yeah, 0 to any power, any positive power is 0. 0 to the 0 is usually defined as 1. That's usually what creates.
To be rigorous is undefined, but the most convenient definition.
Right, because usually that's what results in continuous functions.
Yeah.
It's like x log x. To be rigorous, when x goes to 0, it's undefined.
Yeah, but you define the limit.
But we usually define it as 0 because it tends to agree with.
It's the limit of that.
Right, right,
Would be 0.
right. So I think that yeah, x to the x, when x goes to 0, what's the limit?
1.
This matters more.
No,
So it's as if this go to 0?
You could take the x log x.
Yeah.
Right,
X log
right.
x.
X log x goes to 0, so this goes to 1. Yeah. So this is the argument why.
Yeah, so 0 to the power 0 is undefined because the limit of 0 to the x and x to the 0, their limits are different.
Right. So it depends on what rate you're moving.
Yeah.
But since they're both together, they must be moving together. So I think x to the x, the limit is 1.
Yeah, yes.
Okay. Thank you. Okay, so all this is a way of saying that we often deal with the multinomial in language, not just in words, but in lots of other things, in documents and topics and phrases and alignments. We often deal with a very large space of categories. So we define a multinomial. And the multinomials are almost always sparsely estimated. We don't have nearly as much data to estimate the parameters reliably using relative frequency. So we must use smoothing. And what kind of smoothing you do does matter, makes a big difference. And we went over several standard ways of smoothing and tried to interpret them from a statistical estimation theory point of view. So linear interpolation can be thought of as a shrinkage between different estimators with different bias variance trade-off. And pseudo-counts can be thought of as assuming a Dirichlet prior and then taking the mean of the posterior. We talked about good Turing, which is somewhat orthogonal to the other kinds of smoothing. You could do good Turing smoothing, and then you can also do interpolation. Good Turing is a correction to the maximum likelihood estimator for very small counts. Okay, so we kind of spent a lot of time on this because you're going to run into multinomials everywhere. I want to show you one other method of dealing with sparseness when it comes to a hierarchy of models. So the n-gram can be thought of as a hierarchy of models. For an n-gram, your goal is to estimate probability of word I given word I minus word 1 through word I minus 1. This is the true thing you're after. And what you have in your hands, instead, what we have is P of Wi given only W, say, I minus 3, I minus 2, I minus 1, and P of Wi given Wi minus 2, Wi minus 1, and P of Wi given Wi minus 1, and P of Wi given nothing. And not only that, we don't even have these. We have estimates of these, right? So we are twice removed from what we're really after. Once by assuming an nth order Markov chain. Here is 0 order, here is a first order, second order, third order Markov chain. Assuming that language depends only, the next word depends only on the last few words. And the second thing is we're using estimators from the data, and let's say we use maximum likelihood estimators from the data, or good Turing. Could do either one. Or some other smoother. But the important thing is that we have a set of estimators, and let's assume further that it's not just a set, but it's an ordered set, it's a hierarchy, as is the case here. There's a clear ordering here, such that the bias goes in one direction and the variance goes in another direction. Variance is highest here, and bias is highest here. And the way we decided to combine them was by linear interpolation with weights. And we have a way of estimating the weights based on some held out data. There's another way we can combine them, and that is nonlinearly. So one method is linear interpolation with weights. The second method is nonlinear combination. And the nonlinear combination, you can do the following. You can say, I prefer to use a model that has the smallest possible bias from the ones I have. And this of these has the smallest bias. Right? It's smallest, it's closest, it's most similar to the true thing I'm after than these are. So I prefer to use this as long as its variance is not too large. How do I measure if its variance is too large? I look at the enumerator. So the maximum likelihood estimate of this would be the count of how many times word I minus 3, word I minus 2, word I minus 1, and word I occurred, and divided by the count of how many times I minus 3, I minus 2, I minus 1 occurred. That's my usual estimate for this. If it's the maximum likelihood estimate, if it's the good Turing estimate, it's going to be modified somewhat. So I could set a rule that says that if this count, first of all, if this count is 0, I cannot use this estimator. You pointed out last time, right? Somebody pointed out last time. Something I didn't mention before, that if the denominator is 0, it's not defined. So I can't really use it. But as long as the denominator is not 0, I can use it. But if this count is 0, or 1, or 2, some small number, I may decide not to use this estimator and to back off to this estimator. So I can make a nonlinear decision. If the count of Wi minus 3 through I is less than some constant k1 or k, call it k3, use this model, which is a 4-gram, right? Trigram, bigram, unigram. use the 4-gram. Otherwise, back off to the trigram. And back off to the trigram means that I'm going to ask about the trigram. Otherwise, if the count of wi minus 2, wi minus 1, wi is less than, I'm sorry, this should be greater than, right? You should have corrected me. If it's greater than some constant, then I'm going to use the 4-gram. If it's less than a constant, the constant could be 1 or 2, or even 0. If it's greater than 0, I'd rather use this. These counts are integers, so if it's greater than 0, it's 1 or 2 or more. But I can decide on some kind of a cutoff. If it's greater than the cutoff, I will use this higher order model. If it's not, I will back off and consider the next lower order model. And when I consider the next lower order model, if this is greater than some cutoff, which could be the same cutoff or a different cutoff, then use the trigram. Otherwise, I will back off and consider the next level down. And so forth. I'll keep going down. In the end, I'll get to the 0-gram, which is just 1 over v. In practice, I will probably get stopped at the unigram, because the count in the numerator of the unigram is the count of how many times a particular word occurred, and I'm assuming that all my words occurred. If not, I'll back off to the 0-gram. The idea is this is a different way of combining estimators, a different way of trading off bias and variance. The linear interpolation says I'm going to use all of them, and I'm just going to use them in different weights, different proportions. The nonlinear way says I'm going to start with the least biased one, and as long as its variance is not too high, I will use it. If its variance is too high, and I'm judging the variance size by the count of the numerator, if it's too high, I will back off to the next less lower order model, from 4-gram to trigram to bigram and so forth. This method is defined regardless of whether it's an n-gram. It could be some other hierarchical model. And in fact, it doesn't even have to be strictly hierarchical. It could be, you can use classes, you can use all sorts of things. And there's one detail that I'm hiding here, and you have to normalize things properly. Because for the same context, for the same history, different words will be estimated by different components of these. So you need to make sure that they all normalize and sum to 1. So there's a process of calculating back-off weights. The Slava Katz paper that you looked at when you looked at good Turing introduces this kind of a model, so you can look at the details. In fact, the Slava Katz paper, surprisingly, even though it's just a single, like 2 pages, one paper at both sides, introduces 2 distinct ideas. One of them is good Turing. He didn't invent it. Turing or Good invented it, but he introduces to language modeling. And the other one is this nonlinear combination, which he calls the Beckhoff model. And the Beckhoff model is actually, at the time when it was introduced in the 70s or 80s, was very surprisingly powerful, often beating the linear interpolation model when there was a lot of data, when there was little data. And years later, the general statistical theory of estimation became infatuated with Lasso type models. And if you think about Lasso, it is very strongly related. They're all examples of nonlinear smoothing, in that if you look at the curve of Erov and Lasso, you see that it goes down and then it zeroes out, and another goes down and zeroes out. It makes discrete decisions about which parameters to put in. So in a sense, these people who were not really true statisticians discovered nonlinear smoothing before the mainstream statistical community started working heavily on it. And today, all these Lasso-like methods and ridge regression, all these methods that try to deal with sparse data and large dimensions are coming through and standardizing it and proving all sorts of things. These guys didn't prove anything. They just worked for them. So this reminds me of the distinction I made between machine learning and statistics. You know, do you care that it's right, or do you care that it works, and so forth. Yes?
So this is, you could generalize this like if, else idea into like a back-off model where you have weights on every single model, and if you can say like some weights can just go to 0. So
You can say
would
that.
You would just like not use that term.
Yes. Instead of calling it if-then, you can call it it's a linear interpolation, but the weights are highly dependent on the context. In fact, they're dependent not only on the context, they're also dependent on the word you're about to predict. That's what makes the explicit normalization important. When we did the linear interpolation, one thing I did not mention, but you should know, is that the linear interpolation, the lambdas could depend on the history. So the general form of the linear interpolation model P of word given history is sum of lambda j times pj of the word given history. J goes from 1 to, we said, k. This is the model as I showed it to you, and this is what you played with in your assignment. But in fact, you can make these lambdas depend on the history in any way you want. So for example, for history that was seen many times in the data, you could train a separate set of lambdas. And those are likely to have a high value for the models that have low bias. But for histories that were seen very few times, when you train them separately, you're likely to get a higher weight for, did I say the other way around? Yeah, when you have a history that was seen many, many times, the variance of the estimators is likely to overall be small, and therefore there will be preference for those with low bias. For histories that were seen very few times, there won't be as much. It'll be the other way around, because the differences in variance will prevail. So in fact, you can train many, many different sets of lambdas. The only thing is that for any particular dependence on H, you have to make sure that the entire array of lambdas sums to 1. Now what you were suggesting, Malcolm, is that you can represent the nonlinear thing this way, but then the lambdas depend not only on the history, but also on the word you're predicting. And that requires explicit normalization. This does not require any normalization. As long as the lambdas themselves sum to 1, this is a bona fide distribution. Yes?
For the nonlinear combination, are the k's always distinct from each other at different points? So is K3 always not equal to K2?
No, no, there's no reason for that. The simplest model, the k's will all be 0. If you've seen this 4-gram, you use a 4-gram. Otherwise, you back off to using a trigram. And if you've seen a trigram, you use it. If not, back off to using a bigram. But you might want to use 1 or 2 here. Your upcoming assignment will be to play with the language modeling toolkit. And you will see that there are parameters. The toolkit implements this back-off model. And you will see that these are the main parameters to the model. Okay, I think we talked enough about multinomials, unless we have any parting comments. So what I want to switch to now is to the question of how do we measure the quality of a model. I hinted at it before many times when I said that which optimization criteria you should use depends on what it is that makes you consider something a good approximation. What is a good approximation? And that a very commonly used method in standard statistical estimation is mean squared error of the parameters. So normally statisticians play the following game. They say, suppose somebody knows the distribution, they know the truth, they give you some data from it, you run your proposed estimator, you estimate point estimation of the parameters, they compare your point estimate to the truth, subtract, square it, so they look at the square difference, and repeat the experiment many, many times. And the average of that is how good your method is. That's called the mean squared error measure. Sometimes you can do that analytically. You don't have to run the experiment, because you can simulate what your estimator would say on different possible datas, weigh it properly, and you can calculate the mean squared error of an estimator. But that's not the measure that we care about. I hinted that if the correct value of some parameter is 0.000001, and you gave it the value of 0, a mean squared error measure would think it's an excellent approximation, right? Because the difference between 10 to the negative 7 and 0 is very, very small, and the square of that is even smaller. So it would seem like a reasonable estimate. But for our purposes, actually 0 is a very bad estimate of anything other than 0. So let's take a less extreme example. If you remember, what we said is that we care about the relative error. So suppose you have two parameters you're trying to estimate, theta 1 and theta 2. Theta 1, the true value, is 0.30. And theta 2, the true value, is 0.000001. Well, theta 1 hat estimate is 0.35, and theta hat estimate, theta 2 estimate is 0. This is from your estimator A. And your estimator B does a better job here. And here it says this. Now, which do you prefer, A or B? So if you just did the mean squared error, the contribution of this minus this squared versus this minus this square is negligible relative to what will come from here. Right? It's a very, very small contribution. Whereas the contribution here, this is 0.05 squared, and this is 0.1 squared. This is going to be much smaller. So the mean squared measure will prefer estimator A. We, in language technology, would usually prefer estimator B, because what we care about is the relative error, which here would be 0.4 over 0.3 versus, this is 0.35 over 0.3 versus 0.4 over 0.3, which is not that big of a difference. Here, of course, one of them would be infinite. This one would be infinite. This would be 1. Another way of saying the same thing is that what we look at is the log domain. Looking at a ratio of theta hat to theta is the same as looking at the difference between the log of theta hat and the log of theta. Right? So log of that. So looking at ratios, kind of hand-waving, looking at ratios is like looking at a log domain. And what I claim is that we should really think about the quality of what we do in the log probability domain rather than in the log domain. So let's do, now with this motivation, let's do a detour of about a lecture and a half into information theory. Remind me who of you is in the machine learning class? Okay, so if you want to leave, you're excused. Although we're going to move a little faster than we move there. So in information theory, we define the following quantities. Suppose you have an event has a probability P of occurring. When it occurs, we say that we received this many bits of information. Log of 1 over the probability of the event. Let me justify that. Why this arbitrary definition? Imagine an event that you knew with certainty was about to happen. The sun will rise tomorrow. Since you know it with certainty, you assign it a priori a probability of 1 of happening. You woke up tomorrow and the sun did rise. How much information did you get? Well, the probability of the event is 1. 1 over 1 is 1. Log of 1 is 0. You got 0 bits of information, which makes sense. Something that you knew was going to happen did not surprise you at all. So I use the word surprise. We can also talk about this a bit of information as the amount of surprise. So information equals surprise equals log of 1 over the probability of the event. Let's look at the other extreme, an event that you're guaranteed, that you're sure will not happen. You give it a probability of 0, that you'll win the lottery tomorrow. You're sure it's not going to happen, you give it a probability of 0. It happened. How surprised are you? Well, this is 0. 1 over 0 is infinity. Log of infinity is infinity. You're infinitely surprised, which is not a good thing in life. So don't give events probability 0, right? But it's consistent. Something that you knew was not going to happen surprises you infinitely. Something that you knew is going to happen doesn't surprise you at all. Somewhere in between, you have a coin, let's say a fair coin. It says probability 50-50 of landing on head or tail. So P of head equals P of tail equals 0.5. Now you flip the coin and it landed on head. How much information did you get from the fact that it landed on head? Log of 1 over probability of head, which is 1 over 1/2, right? 1 over 1/2 is 2. What is log of 2?
Is it log base 2?
Thank you. So it depends on the base. I didn't tell you what the base was. So now I have to choose a base. I will choose base 2. So that makes it 1 bit. So by our definition, flipping a coin, a fair coin, if it lands on head, I got 1 bit of information. What happens if it lands on tail? Same thing. I also got 1 bit of information. So before I flip the coin, I know that no matter how it lands, I'm going to get 1 bit of information. And I'm going to be surprised, somewhat, not very surprised, 1 bit is not a lot. And I'm going to be surprised the same amount if it lands on head or on tail. That makes sense. I don't have to choose base 2. What happens if I choose a different base? I get a different numerical answer that differs only by a multiplicative constant. In other words, I change the units of measurement. Instead of measuring it in centimeters, I'm measuring it in inches or meters or feet. So it's not a material difference. The base is just an arbitrary decision of what to call those units. In information theory, we use base 2. Sometimes we use base 3. Sometimes we use base E. Rarely base 10. But so that's the amount of information. Now let's look at an unfair coin. For example, P of head 0.7, P of tail 0.3. Based on this, what is the amount of information I get if the coin landed on head? It is log base 2 of 1 over 0.7, which is log base 2 of about 0.14, no, 1.4 something, about. Is that right? Yeah. Which is, I'm sorry? About 20.5. 0.5 bits. about. What about information if the coil landed on tail? Log base 2 of 1 over 0.3 is about log base 2 of 3.3, which is about how much?
Maybe 1.7.
All right. 1.65, shall we compromise? All right. The important thing to notice here is A, they're different. B, they're different than what we got here, which is always 1 bit. They're on both sides of the 1 bit. The most common answer, which is the head, gave us less information and surprised us less. Surprised us just by half of a bit, whereas the usual fair coin surprised us by a full bit. And the more rare event, the tail, when it occurred, gave us more information or surprised us by a larger than average amount. Now we can ask, how much information does the unfair coin give us on average? Namely, if you flip that coin 100 times in a row, it's the biased coin of 70%, 30%. If you flip it 100 times in a row and communicate the string of results, how much information is that in that string of results, or how surprised are we to learn it? And I don't want to do just 100, I want to do the expected value over arbitrarily long stretches. So I'm asking, what is the expected value of the information in a particular coin flip? Expected value of the information in a 0.7.3 coin. So what does the expected value mean? It means a summation over all possible outcomes, which there are only 2. So I'll write it, well, I can write it like this. I goes from 1 to 2 of the information I get from event I, weighted by how likely event I is. Right? That's what expectation is. It's weighing the outcome by how likely it is to happen. In the case of, this is the general formula. In the case of the coin, it's P of head times the information in head plus P of tail times the information in tail, which is 0.7, that's for the head, right? P of head is 0.7 times 0.5 bits plus 0.3 times 1.65 bits. So basically it's averaging exactly 0.65 and 0.5, which would be 2.15 divided by 2. No, these are not numerically correct estimates, because the average should be less than 1. So somebody with a calculator.
This amounts to 0.8.
Oh, I'm sorry, I did not weigh them properly. Okay, point here or here? Or are you talking about this?
Yeah.
Ah, okay. 0.845. The important thing about this number is that it's less than 1. Why 1? Because in the case of the fair coin, expected value of fair coin is probability of head was 0.5 times the information in head was 1 bit plus probability of tail was also 0.5 times the information in tail is also 1 bit. This basically comes to 1 bit. Since every flip gives me 1 bit, the expected value is 1 bit. In the case of unfair coin, every flip doesn't give me the same amount. Some flips give me more than 1 bit, some flips give me less than 1 bit. The average is less than 1, and that's critical. An non-uniform distribution gives me less information than a uniform distribution. Or you could say the non-uniform distribution contains less surprise or contains less information than a uniform distribution. There's a name for this. If I just consider that the expected value of the information in a particular, what do I call it? Okay, the information according to P of an event, this is a random variable, and I'm looking at its expected value under the same distribution. This is what I did here, right? This is the sum of Pi times information of EI according to the same P, which is sum of Pi times log base 2 of 1 over Pi. I just want to point out that even though it's the same Pi, they came from different sources. This Pi came from our belief about the probability of this event EI. This is critical. It is a subjective measure. It is what we believe about the world that makes us surprised or not surprised. Not how often things happen, but how often do we think they happen. So if something happens that the whole world knows is common, but I think is rare, I'm going to be surprised. The rest of the world is not going to be surprised. So this I measure is subjective. It's relative to my belief about the world. So this is why I wrote this P here. It's the P that drives the information measure. And it's subjective. It's the P that drives this. This P has to do with how often these things actually happen in the world. If I want the true expectation of my surprise, I have to use the true P, if I have it. If I don't have it, I have to estimate it somehow. But this is objective. The distinction is important because at some point we're going to split them apart and say what happens if our belief about the world is different than the true distribution in the world. But for now, let's assume that we know the truth. So we know P. Here and here they're the same. And this is called, of course, the entropy of the distribution P. The entropy is a measure of a distribution. It's a functional. It's something that takes a distribution and produces a number. And the measure of the distribution is defined as this thing. You can just go directly from the word entropy to this thing. It's the usual definition. Another common way of defining it would be to do sum of Pi log Pi. And because we flipped the 1 over Pi to Pi, there's a negative sign that comes out. So you'll often see the entropy defined as negative sum Pi log Pi. I prefer to think about it this way. In fact, I prefer to think about it this way. And in fact, I prefer to think about it this way. I prefer to think about it as the average surprise that someone who knows the distribution experiences, or equivalently, the average amount of information they get. Someone who knows the true distribution Pi. There is a natural generalization of this to continuous distributions. P of x log of 1 over P of x dx, where x is a continuously distributed variable. We're going to stick with this because that's what we usually encounter in language. And what do we know about the properties of entropy? So let's start first with what we know about the properties of information, of the information measure, or surprise. Can surprise be negative? Ooh. Somebody should say something. I'm an absent-minded professor. It's overtime. All right, go home.